Okay, so first the lab. You did the lab today, or the last day you were in class, whenever you're watching this video. But I know some of you said, like, you read it, but you still didn't really have a clue what it was talking about. So let me see if I can help you. Okay, so it says, you know that the direction of the magnetic field at any point around a magnet is indicated by the north pole of a compass. Of course you do, at that point. In this experiment, you will place a bar magnet at one end of a sheet of paper so that the longitudinal axis of the magnet is perpendicular to the north-south line of the classroom, or for us, outside. Okay, so imagine that this is your paper. Okay, so here's your bar magnet. Here's your long line. And then, of course, along this line, you did perpendiculars. Okay, so when we went outside, you took the bar magnet off and you put your compass over here on the line that was furthest away. And then you moved the paper around so that the north of your compass was pointing like this. Okay, so that means north was here, and south was here, and east would be over here. And with the bar magnet far away, the compass was reading the magnetic field of the Earth. Okay, and that's why it was pointing straight north, due north. But now we're going to put the bar magnet back, and as soon as you did, you put the north pole facing here, you should have noticed that the compass needle now moved a little, so it pointed away. Okay, because remember, compass needle doesn't point into the north, it points away. And then you took that reading, and then you moved it here, and you moved it here, and you moved it here. And as you moved it closer and closer, the compass, the field, the compass is reading a balance between the magnetic field of the Earth and the magnetic field of the bar magnet. When you're far enough away, they're kind of in a pretty decent balance. But as you move closer to the bar magnet, its field gets stronger compared to that of the Earth, which doesn't change. And because its field's getting stronger, it's repelling the north pole of the compass more and more and more. Okay? And so when it says one field is that of the bar magnet, which always acts along the axis. So the bar magnet's field lines are going to be like coming out of the north, right? Are going to become out and eventually curve around, which will be at right angles to the Earth's magnetic field if you've lined your paper up right. Okay, so the line showing the axis of the magnet will be extended. Compass placed at any point along the line is acted upon by two magnetic fields at right angles to each other. One is that of the bar magnet that's acting along the line, which we'll call B, so the bar magnet's field is B. And the other one is the horizontal component of the Earth's magnetic field, okay, which is what the compass will be reading. We'll call that one M. All right, and it always acts along the north-south line of that we have the perpendicular line that we found by moving the bar magnet away and lining up the compass. So that's the north-south line of the Earth's magnetic field. Okay, so under the action of the two fields, the compass needle assumes an equilibrium position between them, right? They're both pulling and pushing on it, so it's going to find the equilibrium spot between them. If the theta is the angle between the compass direction and the Earth's north, then as shown in a diagram that doesn't exist, but okay, so the field would be going like this. The Earth's north would be going like this. Your compass needle would be going like this. This angle, theta, here's M. We said we were calling the Earth's field M. We're calling the bar magnet's field B. Oh, and it's measuring the other angle because I drew it the wrong way. I should always read my notes. So here's M. Here's B. Okay? And this is the angle. And that is the one you were measuring. Theta, right? So this is M. This is B. Then tan theta will equal B over M. Ignore this one. Okay? So you were measuring theta. You know m. For us, it's 5.5 times 10 to the negative 5 Teslas. So if you know theta and you know m, you should be able to find the strength of that bar magnet at different spots. Okay? So we're going to measure theta in this lab, and then knowing m, we can compute the magnetic field of the bar magnet at different points as we get closer. Okay? So then it leads into the experiment that you did. And then at the bottom, it says, in results, complete the table. So what should the table look like? Well, the table should be D for the distance, like the 5, 10, 15, 20. It should be theta that you measured. And then it also wants you to find tan theta. And it wants you to find 1 over d squared. Okay? So in the table, that's what you're going to have. Now, watch your, I'll get that to a second. Okay, so that's results number 1. Then it says make a graph plotting tan theta as the ordinate and d as the abscissa. Now to do this, you would need to know which one's the ordinate and which one's the abscissa, wouldn't you? Okay, I'll let you think about that one. And then it also says plot tan theta against 1 over d. Now, this is the part I want to talk about. If you got an angle, like you probably started off with, I don't know, maybe 16, and then maybe 24, and then maybe 38. I'm just making up random numbers here. These are not actually what, it might be 50. But at some point, you probably got like an 89, and maybe even a 90. Don't use these when you go to do your graph, because for these ones, the tan theta is huge. And so then you would do a graph where like all your points would be down here, except for one that would be way up here. So when you get too close to 90, I want you to drop them. So you're probably going to need to drop your 5 centimeter one for sure, and maybe your 10 centimeter one as well. Okay, so I want you to drop, not to plot them. Leave them in the table, but don't plot them on these two graphs. Okay, so on these two graphs, then you're plotting tan theta as the ordinate, and for the first graph, tan theta as the ordinate and distance as the abscissa. In the second graph, you're plotting tan theta against 1 over d squared. Okay? If you can do those things for the next time I see you, have those two graphs, I will be very happy. Because these are usually the two things that screw people up. So part of what you can work on between now and when I see you is those two graphs. And then, of course, the rest of the lab write-up. But I'd like to see those two graphs when you come back to school so that we can deal with the issues when you don't know how to do the scale is what I'm really worried about. And I trust if you don't know which one's the ordinate and which one's the abscissa, you'll look it up. I could tell you, but it will stick in your head longer if you look it up if you don't know it. Okay, so two graphs, please. And now I'll do one new little thing in the physics, in the Science 12.2 world.